Welcome, everyone. In this session, we are going to put Kirchhoff's laws to work by solving a series of practice problems. By now, you have learned the two foundational laws of circuit analysis, Kirchhoff's voltage law, or KVL, which states that the sum of voltages around any closed loop in a circuit is zero, and Kirchhoff's current law, or KCL, which states that the sum of currents entering a node equals the sum of currents leaving that node. We will combine these with Ohm's law to solve circuits step by step. Pay close attention to the polarity markings, the plus and minus signs on each element, because choosing the correct sign is the most common place where students make mistakes. Let's begin. Look at the circuit on the left, labeled A. We have a 20-volt source on the left side, a 2-ohm resistor on top with voltage V1 across it, and a 3-ohm resistor on the right with voltage V2 across it. Notice the polarity markings carefully. For V1, the plus is on the left and the minus is on the right. For V2, the minus is on the top and the plus is on the bottom. Our task is to find V1 and V2. We assume a current I flowing clockwise around the loop, as shown in figure B. Step 1, Ohm's law. For the 2-ohm resistor, the current I enters at the plus terminal of V1, so V1 equals 2 times I, that is, 2I. For the 3-ohm resistor, the current I flows downward, but the plus terminal of V2 is at the bottom, meaning the current actually enters the minus terminal. Because of this opposite polarity, V2 equals negative 3I. Step 2, apply KVL around the loop. Going clockwise and summing voltage drops to 0, we get minus 20 plus V1 minus V2 equals 0. Step 3, substitute. Replace V1 with 2I and V2 with negative 3I. This gives minus 20 plus 2I plus 3I equals 0, which simplifies to 5I equals 20, so I equals 4 amperes. Step 4, final answers. V1 equals 2 times 4, which is 8 volts. V2 equals negative 3 times 4, which is minus 12 volts. The negative sign on V2 tells us that the actual polarity is opposite to what we initially assumed. Verification. Substituting back into KVL, minus 20 plus 8 minus negative 12 equals minus 20 plus 8 plus 12, which equals 0. KVL is satisfied, our answers are correct. Now we have a more interesting circuit, a single loop with 2 voltage sources. On the left is a 32-volt source. On top is a 4-ohm resistor with V1 across it. On the right we have a source labeled minus 8 volts, note carefully that this value is already negative. On the bottom is a 2-ohm resistor with V2. We want to find V1 and V2. Step 1, Ohm's law. Assume current I flows clockwise. For the 4-ohm resistor on top, current enters the plus terminal, so V1 equals 4I. For the 2-ohm resistor on the bottom, the plus is on the left, and the clockwise current flows from right to left across the bottom, so the current enters the minus terminal. Therefore V2 equals minus 2I. Step 2, apply KVL clockwise. Sum of voltages around the loop equals 0, minus 32 plus V1 minus negative 8 minus V2 equals 0. Notice we wrote minus negative 8 because the source value is already negative. The two minus signs preserve the correct sign convention. Step 3, substitute and solve. Plug in V1 equals 4I and V2 equals minus 2I, minus 32 plus 4I plus 8 minus negative 2I equals 0. Combining terms, 6I equals 24, so I equals 4 amperes. Step 4, back substitute. V1 equals 4 times 4, equals 16 volts. V2 equals minus 2 times 4, equals minus 8 volts. Verify. Minus 32 plus 16 plus 8 minus negative 8 equals 0. The circuit checks out. This problem introduces something new, a dependent voltage source. Look at the diamond-shaped symbol on top of the circuit. It represents a source whose value is 2 times V0, where V0 is the voltage across the 6 ohm resistor at the bottom. The output of this source therefore depends on a voltage elsewhere in the circuit, hence the name dependent source. We have a 12-volt independent source on the left, a 4 ohm resistor on top, the dependent source 2V0, a 4-volt independent source on the right, and a 6 ohm resistor on the bottom with voltage V0 across it. We want to find V0 and the current I. Step 1. Apply KVL around the loop, traversing clockwise. Starting from the bottom left corner, -12, plus 4I across the top resistor, plus 2V0 across the dependent source going from plus to minus, -4 for the 4-volt source, plus 6I for the bottom resistor, equals 0. Step 2. Apply Ohm's law to the 6 ohm resistor. Because the clockwise current exits the plus terminal of V0, V0 is negative, V0 equals -6I. Step 3. Substitute and solve. Substitute V0 equals -6I into the KVL equation. This gives -16 plus 10I minus 12I equals 0, or -2I equals 16, so I equals -8 amperes. The negative sign means the actual current flows counterclockwise, opposite to our assumed direction. Step 4. Find V0. V0 equals -6 times -8, which equals positive 48 volts. Verify. Plugging back into KVL, -12 plus 4 times -8 plus 2 times 48 -4 plus 6 times -8 equals 0. This simplifies to -12, -32, plus 96, -4, -48, which adds up to exactly 0. Perfect. Here is another circuit with a dependent source. We have a 70-volt source on the left, a 10 ohm resistor on top with voltage Vx across it, a dependent voltage source on the right whose value is 2Vx, so it depends on the voltage Vx across the 10 ohm resistor, and a 5 ohm resistor on the bottom with voltage V0. We need to find Vx and V0. Step 1. Ohm's law. Let I flow clockwise. Vx equals 10I because current enters the plus terminal of Vx. For the bottom resistor, the plus of V0 is on the left, and the clockwise current enters at the right, the minus side, so V0 equals -5I. Step 2. KVL clockwise, sum of voltages equals 0, -70 plus Vx plus 2Vx plus 5I equals 0. Step 3. Substitute Vx equals 10I -70 plus 10I plus 20I plus 5I equals 0, giving 35I equals 70, so I equals 2 amperes. Step 4. Back substitute. Vx equals 10 times 2 equals 20 volts. V0 equals -5 times 2 equals -10 volts. Verify. -70 plus 20 plus 2 times 20 plus 5 times 2 equals -70 plus 20 plus 40 plus 10, which equals 0. Confirmed. So far we have used KVL to solve loop problems. Now we switch gears and use Kirchhoff's current law, KCL, at a single node. Look at node A at the top of the circuit. 3 branches meet here. On the left is a dependent current source whose value is 0.5 times I0, pointing upward, so it pushes current into node A. In the middle is a 4 ohm resistor carrying current I0 downward, so this current is leaving node A. On the right is an independent 3 ampere current source pointing upward, so 3 amperes enters node A. Our task is to find I0 and V0. Step 1. Apply KCL at node A. Sum of currents entering equals sum of currents leaving. Currents entering, 3 amperes plus 0.5 times I0. Current leaving, I0. So the equation is 3 plus 0.5 I0 equals I0. Step 2. Solve for I0. Rearranging, I0 minus 0.5 I0 equals 3, which gives 0.5 I0 equals 3, so I0 equals 6 amperes. Step 3. Use Ohm's law on the 4 ohm resistor. V0 equals 4 times I0 equals 4 times 6 equals 24 volts. Answers. I0 equals 6 amperes, V0 equals 24 volts. Verify KCL. 3 plus 0.5 times 6 equals 3 plus 3, which equals 6, equal to I0. The currents balance perfectly. This is a parallel circuit. All 4 branches are connected between the same 2 nodes, so they all share the same voltage across them. Let us call this common voltage simply V. The branches are a 9 ampere independent source pointing upward, a 2 ohm resistor, a dependent current source of value 0.25 times I0 pointing downward, and an 8 ohm resistor with voltage V0 across it. The current I0 is defined as the current flowing downward through the 2 ohm resistor. We want V0 and I0. Step 1. Ohm's law on the parallel branches. Since all branches share voltage V through the 2 ohm resistor, I0 equals V divided by 2. Across the 8 ohm resistor, V0 equals V. Step 2. Apply KCL at the top node. The 9 ampere source pushes 9 amperes into the node. Leaving the node are I0 down through the 2 ohm resistor, 0.25 I0 down through the dependent source, and V over 8 down through the 8 ohm resistor. So, I0 plus 0.25 I0 plus V over 8 equals 9. Step 3. Substitute I0 equals V over 2. This gives V over 2 plus 0.25 times V over 2 plus V over 8 equals 9. Simplifying, we get 6V over 8 equals 9, so V equals 12 volts. Step 4. Back substitute. V0 equals V equals 12 volts. I0 equals 12 divided by 2 equals 6 amperes. Verify KCL. Currents leaving the top node, 6 plus 0.25 times 6 plus 12 over 8 equals 6 plus 1.5 plus 1.5 equals 9 amperes, matching the 9 amperes entering. Perfect balance. Now let's bring everything together in a multi-loop circuit. We have a 30-volt source on the left, an 8 ohm resistor carrying current I1 with voltage V1 across it, a 3 ohm resistor carrying I2 downward with V2, and a 6 ohm resistor carrying I3 with V3. Node A is the junction where the 8 ohm, 3 ohm, and 6 ohm branches meet. This circuit has 2 loops, so we will need KCL at node A plus KVL around both loops, together with Ohm's law. Equation 1, Ohm's law. V1 equals 8I1, V2 equals 3I2, V3 equals 6I3. Equation 2, KCL at node A current entering equals currents leaving, I1 equals I2 plus I3. Equation 3, KVL around loop 1, the left loop containing the source, the 8 ohm, and the 3 ohm resistor, 30 equals V1 plus V2, which means 30 equals 8I1 plus 3I2. Solving for I1, I1 equals the quantity 30 minus 3I2, divided by 8. Equation 4, KVL around loop 2, the right loop containing the 3 ohm and the 6 ohm resistors. Since they are in parallel, the voltage across them must be equal, V2 equals V3, so 3I2 equals 6I3, giving I3 equals I2 over 2. Substitution. Substitute equations 3 and the relation for I3 into the KCL equation I1 equals I2 plus I3. After algebra, 30 minus 3I2, all over 8, equals I2 plus I2 over 2, equals 3I2 over 2. Cross-multiplying, 30 minus 3I2 equals 12I2, so I2 equals 2 amperes. Final answers. I1 equals 3 amperes, I2 equals 2 amperes, I3 equals 1 ampere. The voltages are V1 equals 24 volts, V2 equals 6 volts, V3 equals 6 volts. Notice V2 and V3 are equal, as expected for parallel resistors. Our final problem is another two-loop circuit, this time with two independent voltage sources. We have a 10-volt source on the left, a 2-ohm resistor on top with current I1 and voltage V1, an 8-ohm resistor in the middle branch with current I2 flowing downward and voltage V2, a 4-ohm resistor on the right top with current I3 and voltage V3, and a 6-volt source on the right. We want all three currents and all three voltages. Equation 1, Ohm's law. V1 equals 2I1, V2 equals 8I2, V3 equals 4I3. Equation 2, KCL at the top node. I1 entering equals I2 plus I3 leaving, I1 equals I2 plus I3. Equation 3, KVL around loop 1, the left loop. Going clockwise, minus 10 plus V1 plus V2 equals 0, which gives V1 equals 10 minus V2, or 2I1 equals 10 minus 8I2, so I1 equals the quantity 10 minus 8I2, divided by 2. Equation 4, KVL around loop 2, the right loop. Going clockwise, minus V2 plus V3 minus 6 equals 0, so V3 equals V2 plus 6, meaning 4I3 equals 8I2 plus 6, giving I3 equals the quantity 8I2 plus 6, divided by 4. Substitution into KCL. Replace I1 and I3 in equation 2. Open bracket 10 minus 8I2 close bracket divided by 2 equals I2 plus open bracket 8I2 plus 6 close bracket divided by 4. Multiplying through and simplifying, 20 minus 16I2 equals 4I2 plus 8I2 plus 6, which gives 14 equals 28I2, so I2 equals 0.5 amperes, that is, 500 milliamperes. Final answers. Back substituting, I1 equals 3 amperes, I2 equals 500 milliamperes, I3 equals 2.5 amperes. Check the KCL, 3 equals 0.5 plus 2.5, yes. The voltages are V1 equals 6 volts, V2 equals 4 volts, V3 equals 10 volts. We've now covered the complete toolkit for analyzing DC circuits. Let's tie it together. First, Ohm's law, V equals I times R, is what connects current and voltage at every resistor. It's how we convert between the two unknowns in any branch. Second, the polarity convention. When current enters the positive terminal of a resistor, the voltage across it is plus IR. If it enters the negative terminal, it's minus IR. And remember, if you solve and get a negative number, that just means the actual direction is opposite to what you assumed. The math still works. Third, Kirchhoff's voltage law. The sum of voltages around any closed loop is 0. Walk the loop in one direction, add the rises, subtract the drops, or vice versa, and set the total equal to 0. This is what lets you solve single-loop and multi-loop networks. Fourth, Kirchhoff's current law. At every node, the current entering equals the current leaving. It comes straight from conservation of charge, and you'll use it at every junction in a multi-branch circuit. Fifth, dependent sources. Drawn as a diamond, their value depends on another voltage or current in the same circuit. You handle them like any other source, write your equations, then substitute the controlling relation at the end. Finally, the strategy itself. Label all currents and voltage polarities. Apply Ohm's law to every resistor. Write KVL and KCL equations and solve them. Then verify by substituting back. If your numbers satisfy every loop and every node, the solution is correct. Master these three laws, Ohm's, KVL, and KCL, and you can analyze any resistive DC circuit you'll encounter in this course. That's it for Kirchhoff's laws. Thank you.